Welcome to the session Partial Differential Equations Part 2. A differential equation involving two or more independent variables and partial derivatives with respect to them is called a partial differential equation. We will use the following standard notations to denote the partial derivatives. Dou z by dou x is equal to p, dou z by dou y is equal to q, dou square z by dou x square is equal to r, dou square z by dou x dou y is equal to s, dou square z by dou y square is equal to t. Equations which includes at least one of the partial derivatives are st, but none of higher order is called a partial differential equation of second order. In this session, we shall discuss Mungus method, which is a method to solve a nonlinear partial differential equation of the form capital R into R plus capital S into S plus capital T into T is equal to capital V, where capital R, S, T and V are functions of x, y, z, p and q. Equations reducible to partial differential equations with constant coefficients, classification of linear second order partial differential equations and method of separation of variables. Mungus method. Let the nonlinear partial differential equation of the second order be capital R into R plus capital S into S plus capital T into T is equal to V, where capital R, S, T and V are functions of x, y, z, p and q. We have dp is equal to dou p by dou x into dx plus dou p by dou y into dy is equal to r dx plus s dy. dq is equal to dou q by dou x into dx plus dou q by dou y into dy is equal to r dx plus t dy. Solving for r and t, we obtain r is equal to dp minus t dy all divided by dx and t is equal to dq minus s dx all divided by dy. Substituting these values in the given equation, we have capital R into dp dy plus capital T into dq dx minus capital V into dx dy minus s into capital R dy square minus capital S dy dx plus capital T dx square is equal to 0. Let us consider the equations r dy square minus s dy dx plus t dx square is equal to 0 and r dp dy plus t dq dx minus v dx dy is equal to 0, which are known as Mungus equations. Now we have to solve these two equations. First, we shall find the integrals of r dy square minus s dy dx plus t dx square is equal to 0. With the help of these integrals, the integrals of r dp dy plus t dq dx minus v dx dy is equal to 0 are to be found. If necessary, the relation dz is equal to p dx plus q dy can be used. Let u of x, y, z, p, q is equal to a and v of x, y, z, p, q is equal to b be the integrals of the two Mungus equations respectively. Then the general solution of the given equation will be v is equal to phi of u. Example 1. Solve q into 1 plus qr minus p plus q plus 2pq into s plus p into 1 plus p into t is equal to 0. Solution. Comparing it with the standard form, we get capital R is equal to q into 1 plus q, capital S is equal to minus of p plus q plus 2pq, capital T is equal to p into 1 plus p and capital V is equal to 0. Therefore, Mungus equations are q plus q square into dy square plus p plus q plus px into dx dy plus p square into dx square is equal to 0. Let it be equation number 1. And q plus q square into dp dy plus p square into dq dx is equal to 0. Let it be equation number 2. Now, equation 1 can be written as p dx plus q dy into 1 plus p dx plus 1 plus q dy is equal to 0. Therefore, either p dx plus q dy is equal to 0, let it be equation number 3, or 1 plus p into dx plus 1 plus q into dy is equal to 0, let it be equation number 4. From equations 2 and 3, we obtain p plus p square all divided by q plus q square into dq by dp is equal to p by q, which implies dq by 1 plus q is equal to dp by 1 plus p. Integrating log 1 plus q is equal to log 1 plus p minus log c1, which implies 1 plus q all divided by 1 plus p is equal to 1 by c1. Further, equation 4 gives dx plus dy plus p dx plus q dy is equal to 0, which implies dx plus dy plus dz is equal to 0, which implies x plus y plus z is equal to c2. Hence, one of the intermediate integral is 1 plus p all divided by 1 plus q is equal to phi of x plus y plus z, which implies 1 plus p is equal to 1 plus q into phi of x plus y plus z, which implies p minus q into phi of x plus y plus z is equal to phi of x plus y plus z minus 1. Hence, Lagrange's equations are dx divided by 1 is equal to dy divided by minus of phi of x plus y plus z is equal to dz divided by phi of x plus y plus z minus 1, which is equal to dx plus dy plus dz all divided by 0. Therefore, dx plus dy plus dz is equal to 0 implies x plus y plus z is equal to c3. Also, dx by 1 is equal to dy divided by minus of phi of x plus y plus z, which implies minus of phi of c3 dx is equal to dy, which implies y is equal to minus of phi of c3 x plus c4, which implies y plus x into phi of x plus y plus z is equal to psi of x plus y plus z, which is the required solution. Example 2. Solve r minus t into cos square x plus p into tan x is equal to 0. Solution. Comparing the given equation with the standard equation, we get capital R is equal to 1, capital S is equal to 0, capital T is equal to minus cos square x, capital V is equal to minus p tan x. Substituting in Mungus equations, we get dp dy minus cos square x dq dx plus p tan x dx dy is equal to 0. Let it be equation number 1. And dy square minus cos square x dx square is equal to 0. Let it be equation number 2. Equation 2 gives dy minus cos x dx is equal to 0. Let it be equation number 3. dy plus cos x dx is equal to 0. Let it be equation number 4. From equation 3, we have y minus sin x is equal to c1. Again, from equations 3 and 1, we have dp into cos x dx minus cos square x into dq dx plus p tan x into dx into cos x dx is equal to 0. Or dp minus cos x dq plus p tan x dx is equal to 0. Or sec x dp minus dq plus p tan x sec x dx is equal to 0. Or d of p sec x minus dq is equal to 0. Or p sec x minus q is equal to c2. Therefore, p sec x minus q is equal to f of y minus sin x. Let it be equation number 5. Similarly, from equations 4 and 1, we have p sec x plus q is equal to g of y plus sin x. Let it be equation number 6. Solving equations 5 and 6, we have p is equal to half of cos x into f of y minus sin x plus g of y plus sin x. P is equal to half of g of y plus sin x minus f of y minus sin x. Substituting in dz is equal to p dx plus q dy, we have dz is equal to half of cos x into f of y minus sin x plus g of y plus sin x dx plus half of g of y plus sin x minus f of y minus sin x dy, half of g of y plus sin x into dy plus cos x dx minus f of y minus sin x into dy minus cos x dx, or z is equal to half of capital G of y plus sin x minus capital F of y minus sin x, which is the required solution. Equations reducible to partial differential equations with constant coefficients. An equation in which the coefficient of derivative of any order, say k, is a multiple of the variables of the degree k, then it can be reduced to partial differential equation with constant coefficients in the following way. Let small x is equal to e raised to capital X, small y is equal to e raised to capital Y, so that capital X is equal to log x, capital Y is equal to log y. Dou z by dou x is equal to dou z by dou capital X into dou capital X divided by dou x, which is equal to 1 by x into dou z by dou capital X, or x into dou z by dou x is equal to dou z by dou capital X, which implies x into dou by dou x is equal to dou by dou capital X, or x into dou by dou x is equal to capital D, where capital D is equal to dou by dou capital X. Now, x into dou by dou x of x raised to k minus 1 into dou raised to k minus 1 z by dou x raised to k minus 1 is equal to x raised to k into dou raised to k z by dou x raised to k plus k minus 1 into x raised to k minus 1 into dou raised to k minus 1 z by dou x raised to k minus 1, or x raised to k into dou raised to k z by dou x raised to k is equal to x into dou by dou x minus k plus 1 into x raised to k minus 1 into dou raised to k minus 1 z by dou x raised to k minus 1. Putting k is equal to 2, 3, etc., we get x square into dou square z by dou x square is equal to d minus 1 into x into dou z by dou x, which is equal to d minus 1 into d of z. X cube into dou cube z by dou x cube is equal to d minus 2 into x cube into dou square z by dou x square, which is equal to d minus 2 into d minus 1 into d of z, etc. Similarly, y into dou z by dou y is equal to d prime of z, y square into dou square z by dou y square is equal to d prime minus 1 into d prime of z, y cube into dou cube z by dou y cube is equal to d prime minus 2 into d prime minus 1 into d prime of z, etc. And xy into dou square z by dou x dou y is equal to d into d prime of z, etc. Substituting in the given equation, it reduces to phi of d comma d prime of z is equal to capital V, which is an equation with constant coefficients. Example 3. Solve x square into dou square z by dou x square minus 4xy into dou square z by dou x dou y plus 4y square into dou square z by dou y square plus 6y into dou z by dou y is equal to x cube into y raised to 4. Solution. Substituting x is equal to e raised to capital X, y is equal to e raised to capital Y, and denoting capital D is equal to dou by dou capital X and d prime is equal to dou by dou capital Y. The given equation reduces to d into d minus 1 minus 4 into d prime plus 4 into d prime minus 1 into d prime plus 6 into d prime of z is equal to e raised to 3 into capital X plus 4 into capital Y, or d minus 2 d prime into d minus 2 d prime minus 1 of z is equal to e raised to 3 into capital X plus 4 into capital Y. Therefore, the complementary function is z is equal to f1 of capital Y plus 2 into capital X plus e raised to capital X into f2 of capital Y plus 2 into capital X, or z is equal to f1 of log y plus 2 log x plus e raised to log x into f2 of log y plus 2 log x, which is equal to f1 of log y x square plus x into f2 of log y x square, which is equal to g1 of y x square plus x into g2 of y x square. Particular integral pi is equal to 1 by d minus 2 d prime into d minus 2 d prime minus 1 of e raised to 3 into capital X plus 4 into capital Y, which is equal to e raised to 3 into capital X plus 4 into capital Y divided by 3 minus 2 into 4 into 3 minus 2 into 4 minus 1, which is equal to 1 by 30 x cube y raised to 4. Therefore, the complete solution is z is equal to g1 of y x square plus x into g2 of y x square plus 1 by 30 into x cube y raised to 4. Classification of second order linear homogeneous partial differential equation. Consider the second order linear homogeneous partial differential equation a into dou square u by dou x square plus b into dou square u by dou x dou y plus c into dou square u by dou y square plus f of x comma y comma u comma p comma q is equal to 0. Let it be equation number 1, where a, b, c may be constants or functions of x and y, and p is equal to dou u by dou x, q is equal to dou u by dou y. Equation 1 is said to be parabolic equation if b square minus 4ac is equal to 0. Hyperbolic equation if b square minus 4ac is greater than 0, and elliptic equation if b square minus 4ac is less than 0. It is to be noted that the first order terms do not play any role in the classification of the equation. This classification is important for determining the number and type of conditions to be prescribed in order that the problem is well posed and has a unique solution. That is, for an elliptic equation, the function or its derivative will be specified around the entire boundary enclosing a region of interest, whereas for the hyperbolic and parabolic equations, function cannot be specified around an entire boundary. Example 4. Consider the following partial differential equations. First one, 3 into dou square u by dou x square plus 2 into dou square u by dou y square is equal to dou u by dou x plus u. Here a is equal to 3, b is equal to 0, c is equal to 2. Therefore, b square minus 4ac is equal to minus 24, which is less than 0. Hence, the given equation is elliptic. Second one, y into dou square u by dou x square plus 2x into dou square u by dou x dou y plus y into dou square u by dou y square is equal to 0. Here a is equal to y, b is equal to 2x, c is equal to y. Therefore, b square minus 4ac is equal to 4x square minus 4y square, that is equal to 4 into x square minus y square, which is greater than 0 if x greater than y, implies hyperbolic equation, which is less than 0 if x less than y, implies elliptic equation, and is equal to 0 if x is equal to y, implies parabolic equation. Method of separation of variables. This is a powerful technique to solve many of the partial differential equations encountered in physical applications in which the domains of interest are finite. Even though it has limitations, it is widely used. It involves the idea of reducing a partial differential equation to several ordinary differential equations for which there exists a method for solution. Then, by satisfying the initial boundary conditions, a solution to the partial differential equation can be found. Let u be a dependent variable and x comma t be the independent variables. This method assumes that the solution to be the product of two functions, one be a function of x and the other be a function of t. That is, u of x comma t is equal to capital X of x into capital T of t. The use of this function u in the given equation leads to two ordinary differential equations. The following example explains the method. Example 5. Solve the equation dou u by dou x is equal to 2 into dou u by dou t plus u, given that u of x0 is equal to 6 into e raised to minus 3x. Solution. Here u is a function of x and t. Let u is equal to capital X into capital T, where capital X is a function of small x alone and capital T is a function of small t alone, be a solution of the given equation. Then dou u by dou x is equal to x prime into t, dou u by dou t is equal to x into t prime. Substituting in the given equation, we have x prime t is equal to 2 into x into t prime plus x into t, or x prime t is equal to 2 into t prime plus t into x. Separating the variables, we get x prime divided by x is equal to 2 into t prime plus t all divided by t. Since x and t are independent, the equality holds only when both sides are equal to same constant, say k. Therefore, x prime divided by x is equal to k, which implies log capital X is equal to kx plus log c1. That is, log capital X by c1 is equal to kx, or capital X is equal to c1 e raised to kx. And 2 into t prime plus t all divided by t is equal to k implies t prime by t is equal to 1 by 2 into k minus 1. That is, log t is equal to 1 by 2 into k minus 1 into t plus log c2. That is, log t by c2 is equal to 1 by 2 into k minus 1 t, or capital T is equal to c2 into e raised to half of k minus 1 t. Therefore, the solution is u of x comma t is equal to c1 into e raised to kx into c2 into e raised to half of k minus 1 t. Since u of x comma 0 is equal to 6 into e raised to minus 3x, c1 c2 e raised to kx is equal to 6 into e raised to minus 3x, which implies c1 c2 is equal to 6 and k is equal to minus 3. Therefore, the solution satisfying the given condition is u of x comma t is equal to 6 into e raised to minus 3x into c2 into e raised to minus 2t. That is, u of x comma t is equal to 6 into e raised to negative of 3x plus 2t. Note: for physical problems leading second order equation, the constant k has to be considered positive, negative and 0 values. Otherwise, it is taken as non-zero constant. Example 6. Solve x square into dou square u by dou y square plus dou u by dou x is equal to 0 by the method of separation of variables. Solution. Let u is equal to capital X into capital Y, where capital X is a function of small x alone and capital Y is a function of small y alone, be a solution. Then dou u by dou x is equal to x prime y, dou u by dou y is equal to x y prime, and dou square u by dou y square is equal to x y double prime. Substituting in the given equation, we get x square into capital X into capital Y double prime plus capital X prime into capital Y is equal to 0, which implies capital Y double prime divided by capital Y is equal to minus of capital X prime divided by x square into capital X, which holds only when both sides are equal to a constant, since x and y are independent. Case 1. Let the constant be positive, say k square. We obtain two ordinary differential equations as follows. Capital Y double prime minus k square into capital Y is equal to 0 and capital X prime plus k square into x square into capital X is equal to 0, whose solutions are capital Y is equal to c1 into e raised to ky plus c2 into e raised to minus ky, and capital X is equal to c3 into e raised to k square into x cube by 3. Therefore, the general solution of the given equation for positive constant is u of x comma y is equal to c3 into e raised to k square into x cube by 3 into c1 e raised to ky plus c2 e raised to minus ky. Case 2. Let the constant be negative, say minus k square. We obtain two ordinary differential equations as follows. Capital Y double prime plus k square into capital Y is equal to 0 and capital X prime minus k square x square into capital X is equal to 0, whose solutions are capital Y is equal to c1 into cos ky plus c2 into sin ky, and capital X is equal to c3 into e raised to minus k square into x cube by 3. Therefore, the general solution of the given equation for negative constant is u of x comma y is equal to c3 into e raised to minus k square into x cube by 3 into c1 cos ky plus c2 sin ky. Case 3. Let the constant be 0. We obtain two ordinary differential equations. Capital Y double prime is equal to 0 and capital X prime is equal to 0, whose solutions are capital Y is equal to c1y plus c2 and capital X is equal to c3. And the general solution of the given equation is u of x comma y is equal to c1y plus c2 into c3. In practical problems, out of these three solutions, one has to choose the suitable solution by considering the boundary conditions and initial conditions. Let me conclude this session. In this session, we have discussed Mungus method to solve a nonlinear partial differential equation of the form capital R into R plus capital S into S plus capital T into T is equal to capital V, where capital letters R, S, T and V are functions of x, y, z, p and q. We have seen that an equation in which the coefficient of derivative of any order, say k, is a multiple of the variables of the degree k can be reduced to partial differential equation with constant coefficients by substituting x is equal to e raised to capital X, y is equal to e raised to capital Y in the equation. We also discussed the classification of second order linear homogeneous partial differential equations and the method of finding solution by variable separable method. Now you have some questions you may try to answer. First one, solve the following equations by Mungus method. 1. X minus y into xr minus xs minus ys plus yt is equal to x plus y into p minus q. 2. X square r minus y square t is equal to xy. Second one, solve x square r minus 3xys plus 2y square t plus px plus 2qy is equal to x plus 2y. Third one, classify the equation dou square u by dou x square minus dou square u by dou x dou y minus dou square u by dou y square is equal to 0. Fourth one, for what values of the constant k, the equation uxx plus k into uxy plus uyy is equal to 0 elliptic, parabolic, hyperbolic. Fifth one, using the method of separation of variables, solve the following equations. 1. X square into dou u by dou x plus y square into dou u by dou y is equal to 0 with u of 2, 1 is equal to 2 into e raised to x. 2. Dou square u by dou x square plus dou u by dou y is equal to 0. Sixth one, find a solution of the equation dou square u by dou x square is equal to dou u by dou y plus 2u in the form u is equal to f of x into g of y. Solve the equation subject to the conditions u is equal to 0 and dou u by dou x is equal to 1 plus e raised to minus 3y when x is equal to 0 for all values of y. For your further study, you may refer the following books. First one, An Elementary Course in Partial Differential Equations, second edition by T. Amarnath, Narosa Publishing House, New Delhi, 2003. Second one, Ordinary and Partial Differential Equations by M.D. Raisingania, Sultan Chand, New Delhi, 2010. Third one, Differential Equations and Their Applications, second edition by Zafar Hassan, Prentice Hall, New Delhi, 2006. Fourth one, Partial Differential Equations and Integral Transforms by T. Veerarajan, Tata McGraw-Hill, New Delhi, 2004. Fifth one, Advanced Engineering Mathematics by E. Kreisig, John Wiley and Sons, New York, 1999. Hope that you have enjoyed this session. We will meet again with another topic. Thank you.